Good day, everyone. So welcome to the 10th module of our electric circuits theory 1. Okay, so this time we will be talking about inductors. For the last meeting, we discussed about capacitors and its behavior on DC and its series and parallel connection computations. So as a recap, a DC, or rather a capacitor, acts like an open circuit on a DC current, okay, or DC power source. Capacitors and inductors are energy storage devices, okay. So this time we will be talking about inductors. Introduction. So one of the passive element that stores energy in its magnetic field. So any conductor of electric current has inductive properties and may be regarded as an inductor. But a practical inductor is usually formed into a cylindrical coil with many turns of conducting wire to enhance its inductive effect. Okay. Just to highlight the difference between capacitors and inductors, again, a capacitor stores energy in a way that if it is connected to a voltage source, for example, okay, so this is the positive side, this is the negative side. So all the positive charges will be collected on the other plate of the capacitor, and all the negative charges will be collected on the other plate of the capacitor. Okay, so this will not be passing through since this is a DC circuit. And once this connection will be cut off, for example, we have a switch here. If we turn off the switch and then we have, let's say, a load here, or light, for example, or LED, for example. So this is schematic diagram of a LED. So if we will cut off the power, so the energy stored from the capacitor, okay, all these positive charges will be flowing towards the negative plate. So that's how the capacitor stores the energy, okay, by storing charges on its plate. On the other hand, the inductor, okay, so if you have an inductor here, if we have an inductor here, oops, okay, we have a DC source, for example. If this is on, or the switch is on, if this is connected, okay, so the current will be flowing through our inductor. Okay, so this is current. What happens now is this current that passes through the inductor produces magnetic fields. Okay, the magnetic fields are being produced around the inductor. This magnetic field is the energy that being stored, that is being stored. Okay, so if the voltage source or the power source will be cut off from our inductor, okay, so once the power source is cut off from our inductor, this electric field will then be converted to current, and that will be the one that will supply the power to the circuit. Okay, so that's the difference between capacitor and inductor. Again, the capacitor stores charges on its plates. Inductor stores magnetic field from the current that passes through it. Okay? Let's proceed. A practical inductor is usually formed into cylindrical coil. Anyway, any type of conducting material can be an inductor. But for a electric field to be effective, it is usually made by, for example, this is a simple wire. Okay? If you will make coils using this same wire, okay, you will be creating a inductor. This one is a simple wire. Creating coils using this wire, you will be making inductors. Okay? So that's the basic structure of an inductor. Even a slight crook on a wire will cause it to be behaving like a conductor. Inductor, I mean. So let's proceed. So this will be our learning outcomes for this module. So number 1, define and discuss inductors. And then number 2, determine the inductance of an inductor. Okay, so these are the examples of inductors that we have. So this is a simple air wound inductor. Okay, this is a transformer. I'm sure you're familiar with transformers. These are the materials that is used to convert our voltage to another type of or another value of voltage. The most used, or rather the most common transformer that we will be, or that we are encountering in our daily lives, is the transformers from our appliances. Okay, usually dito 20 volts. Okay, to 20 volts from our household power source will be converted to 12 volts. Okay, those types of transformers. Or this is usually for the appliances, but for our digital devices, like the chargers for our phones or our tablets, that is to 22 5 volts or 3.5 volts. Okay, so the purpose of the transformer is either to lower or step up or step down the voltage. Okay, to give you an insight of why is there a step up and why is there a step down transformer. Okay, for example, by the way, this is a these are estimate values. These are not the actual values. Okay, for example, from our power plants, if they will be producing, let's say, 1 kilovolt of voltage, okay, from power plants, this will pass through transformers, stepping it up to around 20 kilovolts or as much as 69 kilovolts. Okay, then this 20 kilovolts will be the one that will be distributed on our electric wires, rather electric distribution that you see in the streets. Okay, so this is around 20 kilovolts. Then from this one, this will pass through another transformer that will go to our household. The transformer that you usually see, the cylindrical one. Let's just search that one. Okay. Anyway, this one that you can usually see on our electric posts. Okay. So the purpose of that is to step down this 20 kilovolts to 220 volts. Okay, that will go to our houses. That's the use of transformers in power distribution. Okay, why do we step up the voltage before distribution? Okay, on higher voltages, the losses when the electricity is traveling through a conductor is very low. That's why we need a very high voltage before we distribute the electricity. Then, of course, for our households, we only need a very not very high value of voltage. So the standard voltage being used in the Philippines is 220. Okay, so that's it. That's it for our transformers. Anyway, these are other examples of conductors. These are also chokes. Chokes are used for frequency purposes. Okay, it can be used in audio or other audio or frequency distribution, like in our cell sites, cell towers. Okay, this is being used to set and preset the frequencies that will be transmitted. Okay, so let's proceed. So for the formal definition, an inductor consists of a coil of conducting wire. The terms coil and choke are also used for inductors. So shown in the figure, schematic symbols for inductors. Okay, so 1A is for air core, 1B is for iron core, and then 1C is for variable iron core. But anyway, most of the time when we see inductors in schematic diagrams, this is the only symbol. This is the most common symbol that is being used regardless of the type. Okay. So this is T, again, the schematic symbol of inductor. So we have different types of inductors here. We'll discuss them one by one. So inductors in tuned circuits. Inductors are used in tuning circuits which are used to select the desired frequency, as I've mentioned. Okay, so either in transmitting or receiving RF or radio frequency waves. Number two, induction motors. So induction motors convert the electrical energy into mechanical energy. So the shaft in the motors will rotate because of the magnetic field produced by the alternating current. Okay, so motors are made up of lots of wire wounds. Okay, so I'm pretty sure you let's see. This one. Okay, so a lot of coil of wires. That is the inside of a motor. So the motor is usually powered by the magnetic fields. Let's proceed. Number three, transformers, as I've explained earlier. So transformer is another popular application of inductors. By combining the inductors of shared magnetic field, we can design a transformer. Transformer is the basic and fundamental component of the power transmission system. Okay. Let's try to discuss more on this transformer, okay, because you might be wondering why. This is how a transformer looks like. Schematic diagram. Okay. Then we have an iron core and secondary coil. Okay, so this is what a transformer looks like. Again, primary coil, secondary coil. Okay. So what happens here is, for example, we power the primary coil with 220 volts AC. Okay. So the current of this source will produce magnetic fields in this primary coil. Okay, so there will be magnetic fields, right? Then these magnetic fields will affect the secondary coil. As we mentioned earlier, the power that is being stored in the inductor is in the form of magnetic fields. So the secondary coil will be affected by these magnetic fields. And since these magnetic fields will affect the secondary coil, okay, it will create its magnetic fields in response, and there will be current that will be flowing in our secondary coil. Okay, so the output voltage of this will depend on the number of coils of this one. Okay, so it should be in ratio. There is a formula for ratio when creating transformers, but we will not be discussing it for now. Maybe in the next topics. Okay, so that's how a transformer works. There is no, again, there is no connection from the primary coil to secondary coil. Everything is powered by the magnetic fields. Okay. If anything, if this will be discussed more, I think you have electromagnetic fields subject. But anyway, let's proceed. So next we have chokes. Okay. So inductors will create an opposite current flow when the alternating current flows through it. This means that inductors will choke the AC current and allows the AC current to pass. This property of inductors is used in power supply circuits where AC supply needs to be converted to DC supply. Okay, so this is one of the more important property of inductor. Okay, it allows DC current and it chokes the AC current. Remember in our capacitor, it's the opposite. The capacitor allows AC but prevents DC. Inductor is the opposite. It allows DC and prevents AC. Okay, take note of that. So what happens here is, usually, in a power supply circuit, usually looks like this. You have your source, then it will pass through a transformer. Okay. Transformer. Then the output will be, it depends if what is needed is DC, it will be, let's call this one. Rectified. Okay. After rectification, okay, so this part, the voltage here is still AC. Okay. But after rectification, this will be now DC. Okay. That's the purpose of rectifiers, to convert from AC to DC. But anyway, sometimes there will be chokes that will be placed in here so that if there will be stray, okay, again, no system is perfect. That's why there will be filters like this. Another term for chokes will be filters. For example, after rectification, it is not a perfect DC. As we've discussed, the perfect DC is just a straight line. But if the output here is somewhat not really a straight line, okay, the purpose of this choke is to not let this AC to pass through, but it lets all the DC pass through. Okay, that's the purpose of chokes. Okay, so I hope that was clear. Let's proceed. So now let's go to the definition or mathematical definition of inductance. Okay, inductance again is the property whereby an inductor exhibits opposition to the change of current flowing through it. It's related to the definition of capacitor. A capacitor exhibits opposition to the change of voltage. The inductance, change of current. Okay, so the voltage across an inductor is equals to L times di over dt. Again, di over dt or the derivative means change. This can also be written as delta. Okay, change. So the purpose of the inductor or the property of the inductor is to exhibit opposition to the change of current flowing through it. Okay. So the voltage is directly proportional to the time rate of the change of current when a current passes through an inductor. As shown in this equation, L, the constant of proportionality, and also called the inductance of a material. The unit of inductance is named Henry, okay? Named in honor of the American inventor Joseph Henry. Next, just like capacitor, so the inductor or the inductor of an inductance is also determined by its physical composition. So in this case, we have L is equals to mu A over L N squared. Okay, so let's identify. L is the inductance in Henry. Okay, mu is the permeability of the core. A is the cross-sectional area. N is the number of turns. And then L is the length of the inductor. Okay? So again, L is equals to mu A over L N squared. I don't have a, they call this one, mnemonics for this. So try your best to make the memorization easier or the familiarization easier. Okay? So Joseph Henry is an American physicist who discovered inductance and constructed an electric motor. So he conducted several experiments on electromagnetism and developed powerful electromagnets that could lift objects weighing thousands of pounds. The unit of inductance was named in his honor. Okay, so this is another equation. So the energy stored in the electric field of the coil is 1/2 Li squared. Remember, recall that for the capacitor, this is 1/2 CV squared. Okay. Let's proceed. So these are the following important properties of an inductor. Number 1, an inductor is a short circuit to DC. Okay. Again, it allows DC to pass. The voltage across an inductor is 0 when the current is constant. Okay. So since the inductor is short circuit to DC, a short circuit has 0 volts. Remember that. So the voltage in DC, the voltage to the inductor is 0. Let's go back to the formula for the voltage of an inductor. Again, L di dt. This is the change in current. Okay? But in DC, there is no change in current. So di over dt is equal to 0. Okay? The current is constant. Again, in DC, the voltage and the current are both constant. Alright? So since constant, the change is 0. So the voltage of an inductor in DC is 0. Okay? For DC. For inductors. Alright? So I'll clear this one. The current through an inductor cannot change instantaneously. An important property of the inductor is the opposition to the change in current flowing through it. However, the voltage across an inductor can change abruptly. Okay, so the current changes in a certain manner, certain pattern. It does not change instantaneously, unlike resistors. Okay, so anyway, let's proceed. Number 3, the ideal inductor does not dissipate energy. It takes power from the circuit when storing energy and returns stored energy previously when delivering power to the circuit. Okay. So we have here a few examples. So let's solve some examples. Okay. So consider the circuit in figure 2. So under DC conditions, find letter A, the value of I, letter B, letter A, the value of I and the VC, voltage in the capacitor, and IL, current on the inductor. Letter B, the energy stored in the capacitor. Okay, so anyway. So let's try to solve this one. 1, 4, 5, 1, 2. So we have a VC voltage we have a 12 volts DC voltage, 12 volts, 154. Okay. So 1 ohm, 5 ohms, 4 ohms, okay, 1 farad capacitor, and then 2 henries. Okay. 2 henries inductor. So we're looking for I, this one, the voltage across the capacitor, and then the current across the inductor. And also the, what's the other one? Energy stored in the capacitor. We might solve for the energy stored in the inductor as well. Let's proceed. Okay, so let's try to analyze. Before we try to solve anything, let's try to analyze. This is DC. Okay? Since this is DC, what are the behaviors, again, of our components in DC? For our capacitor, this acts as an open circuit. Okay? So since open circuit, again, what does open circuit mean? Open circuit means that the current here is 0. Okay? Since this capacitor acts as an open circuit for DC conditions. How about the inductor for DC? Since this is inductor and this is DC, meaning the voltage across the inductor is 0. Okay, so always take note of that. Our inductor acts as a short circuit in DC, so voltage 0. Our capacitor acts as an open circuit, so the current is 0. Always take note of that. Right. So, solving for the current, okay, if we will call this line IC, or the current for the capacitor, using KCL, we can say that I is equals to IC plus IL, but IC is equal to 0 since this is a capacitor and it will be an open circuit for DC. So I is equals to IL. Okay. Since this is open circuit, so this will be the line for our current. Okay, this one. Okay. So we have here KVL. So again, so KVL. So we have here, we will follow the blue line because this is the line that has a current flowing. So 12 volts. So 12 is equal to, okay, so the voltage at 1 ohm resistor plus the voltage at the 5 ohm resistor of 5 ohm. Okay. Plus the voltage of the inductor. But since this is DC, we know that the voltage of the inductor is 0. Okay? Then, for the voltage at the 1 ohm resistor, that will be IR. Okay? So I times 1 ohm plus, this one will be 5. So I times 5 ohms. So this will be 6I, okay, plus 12. So I will be equal to 2 amperes, or also equal to the current at the inductor. Okay, so this will be one of our answers. Current at the inductor is 2 amperes. The next question, I think, is, what's the next question? Voltage across the capacitor. Okay, so VC. In the case of the voltage across the capacitor, since, okay, so please listen to this. Since this is an open circuit, this whole branch here is an open circuit. So the current here is 0. Since the current is 0, so for the voltage on the 4 ohm resistor, okay, where shall I write that one? So the voltage at the 4 ohm resistor will be equal to, okay, so IR, which is, I is 0, this is 0, R is 4 ohms, but since this is 0, so the current or the voltage across the 4 ohm resistor is 0. So whatever the voltage for this whole branch will be equal to the voltage across the capacitor. Okay, so that's the point. This branch is parallel to this branch. If we will rewrite or redraw our circuit to see the parallel branches, or for us to see clearer the parallel branches. So again, this is the 1 ohm resistor. This will be the 5 ohms resistor, this will be the inductor. Okay, 1 ohm, 5 ohms, the 2 Henry inductor. In the case of the branch here, this will be open circuit since this is DC, right? Okay, so whatever the voltage in this branch will be equal to the voltage across this branch. And since this branch is made of the this one, since this branch is equal to, or the voltage of this branch is equal to the voltage, let's say I'll just write voltage of the branch so you won't be confused. Okay, so equal to the voltage of the 4 ohm resistor plus the voltage of the capacitor. Since the 4 ohm resistor again is an open, since this is an open circuit, so current is 0 on this one. So the voltage across the 4 ohm resistor is 0. So therefore, the voltage across this branch will be equal to the voltage across the capacitor. And this branch is parallel to this branch. So whatever the voltage here will be equal to the voltage here. And the current flowing through this one is equal to 2 amperes. Okay. Right, this is 2 amperes. So the voltage of this branch which is equal to the voltage of the capacitor will be equal to, okay, so the voltage at the 5 ohm resistor plus the voltage of the inductor. Okay, so we will write this clearly. VC now, so the voltage across the 5 ohm resistor will be equal to IR, of course, and the voltage across the inductor is L di dt, right? But since this is DC, we know that this is equal to 0. So we will be left with this one. So 2 amperes times 5 ohms. Okay, so VC now will be equal to 10 volts. Okay, so this is equal to the voltage across the capacitor. What else are the questions? I think the next question is the power for both the capacitor and then the inductor, or energy stored, I mean energy stored. So energy stored, W is equals to, for the capacitor, that is 1/2 C V squared. Okay, so we will write this one. What is the value of C again? 1 farad. Okay. Yep. So 1/2, 1 farad. Again, this is the energy stored in the capacitor times V squared. So V, 10 volts squared. Okay, so this will become 1/2 times 100. 1/2 times 100. So the power across the capacitor will be equal to 50 joules, or the energy stored across the capacitor will be 50 joules. For the power across the inductor, so okay, WL will be equal to 1/2 Li squared our inductor is 2 Henries. Our current across the inductor is 2 amperes squared. So this will be equal to, this will be 4, this will be 2. So 8 divided by 2. So 4 joules. Okay. So these are our values. So anyway, let's check. Let's cross check on the module if our work is correct. So first I, we have 2 amperes. Okay. And I is equals to IL, so 2 amperes. Checking. Okay, so correct. 2 amperes. Next, voltage across the capacitor. So the voltage across the capacitor, 10 volts. Okay? 10 volts. All right. Going good so well. Energy stored in the capacitor, 50 joules. 50 joules. Okay? Nice. Lastly, energy stored in the conductor, 4 joules. 4 joules. All right. So we got everything correct so far. Again, if you have questions, drop it in the chat box. Anyway, let's proceed. So we have parallel and series inductors. Okay, so this one is not really that hard to memorize because it is the same with resistor. So I'll just make a, what do you call this one? I'll just make a summary here for resistor, capacitor, and inductor for you. Okay. So parallel, series. Okay. So for the parallel of the resistor, so R equivalent will be equal to, this is EQ for equivalent, 1 over R1 plus you might be asking why my formula is looking different from the formula that you use in the module. What they usually do in the module if they are solving for 2 resistor, they are showing you the formula for 2 resistors only. If they will be solving 3 resistors, they will be showing you a formula for 3 resistors only. Okay, so this general formula works for any number of resistors. Okay, you can just add it in the denominator. So that's why I've been using this formula and I've been showing this formula to you. Okay, for the series, that will be R1 plus R2 plus Rn. Okay, so you can add as many resistors as you can for the series equivalent. For the inductor, or let's go to the capacitors first. For the capacitor, which is what we discussed last meeting, so it is the opposite of the resistor. So the series for the capacitor is the parallel for the resistor, and so on and so forth. So for the parallel capacitors, okay, equivalent capacitance is equal to C1 plus C2 plus as many capacitors as we can. Okay? So again, the capacitor is the opposite for resistor. Next, for the series capacitors, the equivalent capacitance will be equal to, right, 1 over C1 plus 1 over C2 plus 1 over Cn. Okay? While for the inductor, that is the same with the resistance or resistors. For the parallel, so only the capacitor has or only the capacitor is different among the three. For the series inductor, all right. All right. Are we good with this one? I hope we're good with this one. So I made you a summary for easier comparison between the parallel and series computations of the three components: resistor, inductors, and capacitors. Again, resistors and inductors the same. Capacitor opposite of the two. All right. So let's proceed. So find the equivalent inductance of the circuit in figure 6. So we have this one. Same method. Start from the what you call this one? Start from the endmost, going backwards. Okay. So we have this one. We have a branch here. So we have a branch here, and we have 3 series inductors. So this will be equal to, we have 4, we have 7, we have 8. Then this 3 will be in series. So we can simplify this. Okay. So 4 Henrys, 7 Henrys, 8 Henrys. So this one will be, since these are in series, so we can add 20 plus 12 plus 10, 42 Henrys. Okay, so next, these are in parallel, 7 and 42. So parallel between 7 and 42 equals, this symbol is for parallel. 1 over 7 plus 1 over 42. So the parallel of 42 and 7 will be equal to, okay, so let's take out our scientific calculators. So 1 over 7 plus 1 over 42 should be equal to 6 Henrys. Okay, so to simplify this circuit, okay, we will have this one. This will be 4 Henrys, this will be 6 Henrys, this will be 8 Henrys, and these 3 are in series, so the equivalent inductor of the whole circuit will be 4 Henrys plus 6 plus 8, so this is 18 Henrys. Okay, so the same as how we solve our resistors. All right. So take a screenshot or take some moment to sort this one. So this is the same solution as we do with our resistors. Okay. So I'll clear this one and let's see if our answer is correct. Okay. Also the module says a step-by-step solution. So I'll clear this one. Right. So 42, then 6, then series, and the equivalent. Okay. Where's the final answer? There's no final answer. They did not write the final answer. My goodness. Now, so the final answer is 18 Henries. So let's proceed to our next example. So find the equivalent inductance of the circuit in this figure. Okay, so this is a classic parallel series problem. So again, let's work our way backwards. Okay. So let's start with this one. We have a branch here. Therefore, this one will be in series. Okay. So this will be 60. Right. So this will be 60. Then this will be parallel. So 1 over 30 plus 1 over 60. This will become 20 millihenries. Okay. Right. Next, we have here 100 millihenries and 20 millihenries in series. So this will be equal to 120. Okay. Next, we have 120 and 40 in parallel. Should be equal to 30. Okay. Next, we have 20 and 30 in series, which will be equal to 50. Then 50 parallel to each other. So the equivalent is 25 millihenries. Okay. So that's it. That's for our series and parallel inductors. Okay. So that's the end of our